I got friends in New York City, 'cause everyone I know left town.
Hi, I'm John. I'm a chemistry graduate student at UCLA, and now in this video we're going to be going over some chemistry topics. Hope you find this useful, and good luck in your course.
So, a 45-degree pulse gives all of the carbons with attached protons, regardless of the number in phase, and I'll explain what that means in just a moment. 90-degree pulses gives only CH groups, and 135-degree pulses gives all CH and CH3 in phase, and opposite to carbons that have two hydrogens attached to them. And so again, this helps you differentiate between carbons with 1, 2, or 3, or 0 protons attached to them. So the actual physics that are responsible for how this technique works probably isn't that important for this. It's a bit beyond the scope of this course. However, it's very easy to interpret these spectra, and given them in a problem or an exam, it's very useful to determine molecular structure. So let me explain a little bit about what it means by in phase or out of phase. And so this is what your typical spectrum would look like with chemical shift on the bottom here, x-axis. When it says that your signals are going to be in phase or opposite phase to one another, what that simply means is this, is that I'm only going to draw a line here, but remember they are actually peaks that you can integrate. Two signals, two carbon-13 NMR signals that are pointing up like this would be in phase to one another, whereas one might be pointing down like this one. So in a typical carbon-13 NMR spectrum, you're not going to see this. They're all going to have your signals pointing up, just like proton NMR. However, if you have depth spectra, the DEPT, depending on the angle of the pulse of the radio frequency in which was used to acquire the data, you might have peaks pointing down like this. So now let's look at an example to really show how you can interpret a molecular structure from this. So now let's take a look at these series of carbon-13 NMR spectra for this molecule here. So this is an isobutyl butyrate. And now let's see if we can label what each of these NMR spectra correspond to, namely the 45-degree, 90-degree, and 135-degree. And so here I have another way that you can really think about this in terms of being in phase or opposite phase to one another. And so a depth 135 spectra, a depth 90 spectra, and a depth 45 can be distinguished from one another based on the types and the phase of the signals that they give. And so again, this all is determined by the number of carbons that are attached, or the number of hydrogens that are attached to each carbon. And so I have here a chart that labels for carbons with 0, 1, 3 hydrogens attached to them for the different depth spectra, whether or not they're going to show a signal at all, or whether they're going to be pointing up or down. If they are, so if this is a depth 45 spectra, you use a 45-degree pulse, and so all carbons with attached protons are going to be shown in phase with one another. So they're all going to be up. Carbons with 0 hydrogens will have 0 signal there in that spectrum. For the depth 90, this will only give us CH groups, and so only carbons that have 1 proton attached to them are going to be shown in here. And then depth 135 gives all CH and CH3 in phase, and so that's why this is up and this is up, opposite to CH2. So carbons that have 2 protons attached is going to give a signal pointing down. So let's look at an example. So this molecule here is 4-hydroxy, 3-methyl, 2-butanone. And we have on the right-hand side a series of 4 spectra. So the bottom one is the full carbon-13 NMR spectrum. And then each one of these, so let's now look at an example. So I have here the molecular structure of 4-hydroxy, 3-methyl, 2-butanone. And then on the right-hand side, 4 different spectra. So the one at the bottom is the regular carbon-13 NMR spectrum. And then these top three correspond to depth 135, 90, and 45. And so let's try to pick out, label each one of these peaks and then label what each one of these spectra correspond to. So first I'll go ahead and say that these three lines right here correspond to the solvent in this particular example, and so we're not really going to worry about that. Okay, so let's try to label what each of these carbons are in these spectra. So we know from before that the carbonyl carbons are going to be the furthest shifted, and so this guy we're going to label as carbon A. We know that this is the carbonyl carbon, A. The sp3 methyl carbons here we can label as B and C are going to be those here in the spectrum with the lowest chemical shift. Here B and C. Refer to the tables before for noting the ranges of the chemical shifts that you should expect for these different carbons. And then D and E carbons should correspond here. D and E. So the first thing that we can recognize here, the carbonyl carbon, A, does not have any protons bound to it, and so that's why in these three depth spectra, the signal does not appear at all in this region. So all the chemical shifts, remember, in each of these depth spectra are going to be the exact same. It just is a matter of whether or not the peaks show up and what phase they're in. Now, we know that carbon E here has only one proton attached. And we know that depth 90 or 90-degree pulse spectra only give CH groups. And so if we look at this middle spectrum here, we see that there's only one peak in the exact position corresponding to our E carbon that has one proton attached. So we know that this is the depth 90 spectrum. We know that depth 45 spectra give all carbons that have protons attached to them, all in the same phase, and so all up. And we can see here this bottom one, A is missing, but all four of the other ones are there, and so we know that this is the depth 45. And so then all we're left with is depth 135. And so here we see that carbon D is pointing down. Carbon D has two protons attached to it, whereas the other three peaks corresponding to carbons B, C, and E are all pointing up. And so again, remember that carbons with one proton and three protons are all in the same phase, all pointing up. And so given this information in a problem, it helps you pick out exactly the number of carbons with 0, 1, 2, and 3 hydrogens attached. And so it's a very useful technique.